Nonlinear buckling analysis is essential in civil and mechanical engineering. Hello, I'm Armin. In this tutorial, I will explore both linear and nonlinear buckling analysis of a cylindrical shell using static structural analysis for the nonlinear response and the eigenvalue buckling solver to obtain the linear buckling modes and introduce geometric imperfection. Let's move on to the model description. Buckling is the sudden loss of stability of a structural member subjected to a compressive load, resulting in large lateral deformations at a critical value known as the buckling load. Linear buckling analysis is an idealized approach that uses an eigenvalue solver to estimate the critical load. As a result, the predicted critical load is usually slightly higher than the actual value observed in reality. Consider a cylindrical shell placed between two jaws that compress the shell axially. The shell exhibits circumferential buckling modes and may buckle when subjected only to an axial compressive load. In reality, the geometry contains imperfections, but in numerical modeling, the geometry is assumed to be perfect. Therefore, a geometric imperfection must be introduced in the model. The lower jaw is fixed, and the upper jaw is allowed to move only in the y direction to compress the shell. The geometry consists of a cylindrical shell with a diameter of 100 millimeters, a height of 250 millimeters, and a shell thickness of 1 millimeter, including two end caps with a thickness of 8 millimeters. The boundary conditions are defined in the static structural analysis. A compressive load of 1 Newton is applied to the upper side of the cylinder, while the lower side is fully fixed. The static structural system is then coupled with the eigenvalue buckling system to determine the linear critical buckling load. Next, the eigenvalue buckling mode is used as a geometric imperfection in a new static structural analysis. The mode shape scale factor is set to 0.01, and the cylinder is compressed by 10 millimeters to trigger buckling behavior. The critical buckling load is calculated from the reaction force at the base of the cylinder. Finally, I will play the buckling animation and calculate the critical load. The results show that the nonlinear critical load is slightly smaller than the linear buckling load due to geometric imperfection. This explanation is sufficient. Let's start the modeling. For buckling analysis, we need two modules: static structural and eigenvalue buckling. Note that eigenvalue buckling is a solver and no boundary conditions are defined directly in this system. Therefore, we start with the static structural module, where all boundary conditions must be specified. I double-click on static structural. In engineering data, we can specify the material. The engineering data library contains many materials. The default material is structural steel and I do not change it, so I close this window. The next step is to create the geometry. I right-click on Geometry and select New Space Claim Geometry. I want to create a thin cylinder. In Space Claim, I click on Circle and select the origin of the coordinate system. I type 100 millimeters as the diameter and press Enter. Then click on End Sketch Editing to close the sketch. Now I want to create a cylinder with a height of 250 millimeters. I click on the cross-section, type 250 and press Enter. I press Escape twice to exit the 3D mode. I need only the surfaces of the cylinder, so I copy the cylindrical surfaces. I select the lateral surface, press Ctrl-C, then Ctrl-V. I repeat this process for the upper surface and the bottom surface. After that, I delete the solid body from the structure tree, leaving only the surfaces. Now, I want to define the thickness for each surface. I select the first surface, and in the Properties window, I set the thickness to 1 millimeter and press Enter. For the upper and bottom surfaces, I set the thickness to 8 millimeters for both, similar to the previous step. As you can see, the thickness values appear on the right side of each surface. These three surfaces are separate, and I want to connect them using shared topology. If shared topology is not used, ANSYS Mechanical automatically creates contact definitions between the surfaces. I'll open the Workbench tab, select Share, and click the green checkmark. Everything looks correct, so I close SpaceClaim. The next step is to define the boundary conditions. I double-click on the Model cell to open ANSYS Mechanical. In ANSYS Mechanical, I expand Geometry in the outline tree, and we can see three surfaces. If I select a surface, its thickness and material are displayed. The material can be changed from engineering data or by using the filter, but I keep it unchanged. I collapse the Geometry node and move to Mesh. The default element size is too coarse, so I set the global element size to 6 mm. Then I right-click on Mesh and select Generate Mesh. This mesh size is suitable for this model. Note that there are no contact definitions between the surfaces because shared topology was used in SpaceClaim. It's now time to define the boundary conditions. I right-click on Static Structural and select Fixed Support from the Insert menu. I select the bottom surface of the cylinder and click Apply. I press the H key to view the model in isometric view. Next, I apply a force on the top surface. I right-click on Static Structural and select Force. I choose the upper surface and click Apply. Then, in the Details window, I change the definition to Components and specify -1 Newton in the Y direction and press Enter. As you can see, the red arrow indicating the force is pointing in the negative Y direction. Everything is correct. Now let's solve the model. I right-click on Static Structural and select Solve. The solution is completed successfully. Now let's check the deformation results. I right-click on Solution, go to the Insert menu, and select Total Deformation. Then I right-click on Total Deformation and choose Evaluate All Results. Here is the deformation result. The deformation is very small because the applied force is only 1 Newton. We can also play the animation to better visualize the deformation. The static structural analysis is now finished. Next, we use the Eigenvalue Buckling solver to find the linear buckling mode shapes. First, I close Static Structural, then drag the Eigenvalue Buckling system and drop it onto the solution cell of Static Structural. Finally, I double-click on the Setup cell of Eigenvalue Buckling to open ANSYS Mechanical. We are now in ANSYS Mechanical. Before solving, the static structural solution must be updated, so I right-click on Static Structural and solve it again. After that, I right-click on Eigenvalue Buckling and select Solve. No additional setup is required. The solution is complete. If I expand the solution branch, we can see the first and second buckling modes. Because the geometry is symmetric about the XY and YZ planes, the first and second buckling modes are identical. I right-click on the first mode in the tabular data, select Create Mode Shape Result, then right-click on it and choose Evaluate All Results. This is the first buckling mode shape. The load multiplier represents the maximum load factor that the cylinder can carry without buckling. If the applied force reaches this value, buckling will occur. Note that this value is multiplied by the reference load of 1 Newton. If we apply 2 newtons or 3 newtons instead of 1 Newton, this value will be divided by 2 or 3 respectively. Now I want to perform a nonlinear buckling analysis. Because the geometry is perfect in the finite element model, the cylinder may compress without buckling, so we need to introduce a geometric imperfection before applying the load. We can use the linear buckling mode shape as a geometric imperfection for the nonlinear analysis. This approach is commonly used in finite element software. I close the Eigenvalue Buckling system and add another static structural system. I drag the solution cell from Eigenvalue Buckling and drop it onto the model cell of the new static structural system. I also share the engineering data. By default, structural steel is assigned. However, if a different material is used and not shared correctly, the static structural analysis may encounter an error. To view the solution properties, I right-click on the solution cell and select Properties. In the Properties window, we can see the mode number and scale factor, which are used to define the geometric imperfection. The mode number is set to 1 because the first buckling mode is required. The scale factor is too large by default, so I reduce it to a small value, for example 0.01. It's recommended to change this value slightly and rerun the analysis to check the sensitivity of the results. If the results do not change significantly, the solution can be considered valid. For many simulations, this value works well. Note that the actual buckling displacement is unknown because eigenvalue buckling is similar to modal analysis. Now I update the eigenvalue buckling system. The static structural analysis now uses the buckling mode shape as a geometric imperfection. I double-click on the model cell to open ANSYS Mechanical. As you can see, the geometry, mesh, and material are imported from the eigenvalue buckling system. We only need to define the boundary conditions again. Boundary conditions must be compatible with the eigenvalue buckling module. Just like before, I apply a fixed support to the bottom surface of the cylinder. I right-click on Static Structural, select Fixed Support, choose the bottom surface, and click Apply. Then I press the H key to view the model in isometric view. There are two ways to apply loading: force and displacement. Displacement control is more stable than force control because after buckling occurs, force-controlled solutions often become unstable. At this stage, large deformations can occur within a very small time step. Therefore, I use displacement instead of force. I right-click on Static Structural, go to the Insert menu, and select Displacement. I select the top surface and click Apply. The direction of the displacement must be the same as the force direction used in the first static structural analysis, so I set the displacement to 0 in the x and z directions. For the y direction, I specify an arbitrary but reasonable value, for example, minus 0.01 meters, and press Enter. This value is reasonable and allows accurate buckling behavior to develop. The next step is enabling large deflection because this is a nonlinear analysis. I click on Analysis Settings and enable Large Deflection. For better convergence, I also enable Auto Time Stepping and set Initial Substeps 25, Minimum Substeps 25, Maximum Substeps 1000. Then I press Enter. Now I right-click on Static Structural and select Solve. If the solution diverges, do not worry. This is common in nonlinear buckling analyses. In this case, the solution diverges, so I show how to fix it. I click on Analysis Settings, go to Nonlinear Controls, and enable Stabilization. I change the Program Controlled option to Constant. It is recommended to use the energy method and activate stabilization only after the first non-convergent step. This means stabilization is applied only when convergence problems occur. Now I solve the model again without changing the default stabilization values. I right-click on Static Structural and select Solve. You can also improve stability by using a smaller displacement value, for example 5 mm or 6 mm instead of 10 mm. This time, the solution converges successfully. Now, let's check the deformation results. I insert total deformation, right-click on it, and select Evaluate All Results. Here is the nonlinear buckling deformation. As you can see, the buckling behavior is captured correctly. If we compare the deformation shape, the nonlinear buckling mode is consistent with the linear eigenvalue mode shape. Now, the important question is, how can we extract the critical buckling force? Buckling occurs at the point where the structure suddenly becomes soft and deformation increases rapidly. A reliable way to calculate the critical force is to use the reaction force at the fixed support. I'll drag the fixed support and displacement onto the solution node to see the reaction. Then I right-click on Solution and select Evaluate All Results. If I click on Reaction Force, we can see the force time curve. The critical force is approximately 6.33 times 10 to the power of 5 newtons. This point corresponds to the onset of buckling. Before this point, there is no significant buckling, but after it, large deformations appear suddenly, which is consistent with the buckling mode shape. Let's look at the deformation shortly after the critical load. After this point, the displacement becomes significant. Let's play the animation once again. If we compare this reaction force-based value with the displacement-controlled result, the two values are nearly identical. The nonlinear critical buckling load is always less than or equal to the linear eigenvalue buckling load, which is physically reasonable. I'll go back to the linear eigenvalue buckling result to compare the linear and nonlinear results. As shown in the tabular data, the linear critical load is slightly higher than the nonlinear one because the nonlinear analysis includes geometric imperfections. That's the end of this tutorial. I hope it was helpful. Thank you for watching.